On August 17, 1943, high over Schweinfurt, Germany, at 27,000 feet, First Lieutenant Curtis Elm leaned forward in the narrow bombardier's compartment of his B-17 Flying Fortress. His hands rested on the controls of one of the most secret devices in the American military arsenal. Through the plexiglass nose, he stared intently at the factories below, the machines that kept Germany's war effort running. Behind him, a formation of 230 B-17s held perfect positions. Each bombardier trusted the same instrument. They all swore they would destroy it rather than let it fall into enemy hands. The orders were clear. If capture seemed likely, drop a thermite grenade inside the device. If that failed, shoot it with your sidearm. If necessary, die protecting it. For those crews, the device was worth more than their lives, more than their aircraft, and perhaps even more than the mission itself. What made this 20-pound assembly of mirrors and gyroscopes so valuable that 12,000 American bombardiers carried loaded pistols just to protect it? Why did the U.S. government treat it as more secret than the earliest stages of the Manhattan Project? And why did its inventor face accusations of treason even though his device helped win the war? The answers lie along a thin, blurry line between genius, passion, patriotism, and criminal behavior. The inventor was Carl Lucas Norden, a Dutch immigrant who spoke little English upon his arrival in America. Norden built a device that changed warfare forever, but he developed it by breaking rules. He violated his employment contract, used company time and materials for private work, spent research funds intended for other purposes, and built and tested a weapon without authorization, actions that likely broke several federal laws. The Norden bombsight should never have existed by the book. Its creation was illegal, its development unauthorized, and its tests were secret. Yet this illicit invention would deliver over 1 million tons of bombs on target with unprecedented accuracy, cripple German industrial capacity, and prove that precision strategic bombing could win wars. This is the story of how an engineer's illegal passion became America's most closely guarded secret weapon. The story does not begin in America, but in Breda, the Netherlands. Carl Lucas Norden was born there on April 23, 1880. The son of a well-to-do family, Norden showed early skill in mechanical engineering and mathematics. He went to study precision engineering and optics at the prestigious Swiss Federal Institute of Technology in Zurich, the same school that later produced many Nobel laureates. At Zurich, Norden developed an almost religious obsession with mechanical precision. At 24 in 1904, Norden emigrated to the United States. He arrived at Ellis Island with engineering credentials and limited English. He found work at the Cramp Shipbuilding Company in Philadelphia. Norden's big break came in 1911 when he joined the Sperry Gyroscope Company in Brooklyn, New York. Elmer Sperry, one of America's leading inventors, had founded the company to commercialize gyroscopic compasses and stabilization systems. Hired as a design engineer, Norden quickly became one of Sperry's most valuable employees. For 8 years, he worked on naval fire control systems, gyroscopic stabilizers, and navigation instruments. The U.S. Navy contracted Sperry to develop improved bombsights for its new aircraft, and Norden led much of that work. He became deeply familiar with bombing problems, how aircraft move in 3 dimensions, how altitude and wind affect a bomb's path, airflow, target movement, and the ballistics of bombs. He also saw how inadequate existing solutions were. But in 1915, while still on Sperry's payroll, Norden began secret work on his own bombsight design. He used Sperry's facilities for hours at a time, used company materials and research from Navy contracts, and tested prototypes with Sperry equipment, all without permission. All of it violated his employment contract and was, technically, illegal. When Sperry discovered Norden's unauthorized project in early 1915, the company faced a dilemma. Norden was their best engineer, but he had clearly broken his agreement. Sperry could sue him, fire him, or negotiate. They chose negotiation. Norden resigned in 1915 and took his designs with him. Sperry decided not to sue, perhaps to avoid publicizing a security failure. Norden immediately opened a small workshop in Lower Manhattan under the name Carl L. Norden, Incorporated. He had no capital, no contracts, and legally, he He had few rights to the technology he planned to commercialize, because much of his work had used Sperry's time and resources. But he had something more valuable, a vision for a bomb sight so precise it could hit a pickle barrel from 25,000 feet. The technical challenge was huge. Existing bomb sights were crude devices, basically calibrated telescopes that helped bombardiers guess when to release their bombs. They worked okay against large targets like warships, but they were useless for hitting specific buildings or facilities. Accuracy was measured in hundreds of yards at best. Most bombs landed within half a mile of their aim, many missed by miles. Norden saw that accurate bombing required solving many complex problems at once. A bomb sight needed to account for aircraft altitude, wind speed and direction, the bomb's ballistics, including terminal velocity and airflow, the aircraft's heading and speed, the target's motion if it moved, and atmospheric conditions at different altitudes. No existing mechanical computer could solve all those equations in real time while compensating for the plane's movement. Norden's solution was revolutionary. He built a mechanical analog computer using precise gears, gyroscopes, and optics that could automatically stabilize itself against the plane's motion and continuously compute the bombing solution. During a bombing run, the device would physically steer the aircraft, while the bombardier used the bomb sight controls to make tiny adjustments. Those adjustments were sent as electrical signals to the autopilot, which nudged the plane onto the exact path needed. At the heart of the system was a gyroscopically stabilized platform that stayed perfectly level regardless of the plane's attitude. Mounted on that platform was a complex mechanical computer that used a train of gears to calculate the bomb run solution. The bombardier entered data with precise dials, altitude from an altimeter, airspeed from the airspeed indicator, wind estimates, and drift from observations. The device then calculated the exact moment to release the bombs. Norden's most radical advance was linking the bomb sight directly to the aircraft's autopilot. That removed pilot error, the biggest variable in bombing accuracy. The bombardier could make microscopic corrections up to the release moment, and the autopilot would keep the aircraft exactly on course. The engineering required pushed 1920s precision manufacturing to its limits. The main gear train had 58 gears, each machined to tolerances of 1/10,000th of an inch. The gyroscopes needed to spin at precisely controlled speeds using small electric motors. The optical system required mirror and lens alignment to within a few arcseconds. The whole mechanism needed to work reliably in conditions from -40°F to +100°F, under vibration, acceleration, and combat damage. Norden spent 5 obsessive years, from about 1915 to 1920, building the first workable prototype. He worked nearly constantly, often sleeping in his workshop. He mortgaged his house to fund development. His personal finances were insecure. Sometimes, he had no income except occasional consulting. His wife, Maria, helped by using her teaching salary to support them. Because of the unclear intellectual property situation with Sperry, where much of Norden's early work had been done, he had no military contracts, no government funding, and fragile legal standing while he designed a military weapon. In 1920, Norden brought his prototype to the U.S. Navy. The Navy's Bureau of Ordnance, desperate for a more accurate bomb sight, agreed to test it. The results were striking. In controlled trials, Norden's prototype proved 10 times more accurate than existing systems. Bombs dropped from 10,000 feet landed within 50 feet of the target. This was a revolutionary improvement. The Navy immediately classified the device and awarded Norden a development contract, but with conditions. All further development had to be done under military security. All technical details were to be kept secret and classified. All testing had to occur at Navy facilities under observation. And before full production could begin, the intellectual property issues with Sperry Gyroscope Company had to be resolved. Sperry's position was delicate. Norden's bomb sight clearly included ideas and parts he had worked on while employed at Sperry. Some components came straight from Sperry's military contracts. Sperry could have claimed ownership of the whole invention or at least sued to stop its manufacture. The Navy needed a better bomb sight. Sperry wanted compensation. Norden wanted credit for his invention. By 1921-22, the solution being discussed was unlike anything before. The the Navy agreed to set up a joint arrangement between Norden's company and Sperry. Sperry would handle manufacturing in its factory, because Norden's tiny shop in Lower Manhattan could not produce parts at the needed scale. Norden would keep design control and earn royalties. Sperry would run production and take a manufacturing fee. The Navy would hold the rights and enforce security. This 1923 agreement created one of history's stranger military contract setups. Carl L. Norden, Incorporated, would design the bomb sights. The Sperry Gyroscope Company would build them. The Navy would control everything and classify all work at an unusually high level for peacetime development. Workers who made parts were not told what they were building. Components were gathered in guarded locations. Fully assembled bomb sights were transported in locked crates under military escort. Development continued through the 1920s. The Navy adopted Norden's Mark I bomb sight in 1924, and it equipped torpedo bombers and patrol planes. In 1929, the Mark 1.15 added temperature compensation and improved gyroscopes. Each new version increased accuracy and reliability. By 1932, Navy bombardiers could consistently place bombs within 100 feet of the target from 15,000 feet. The accuracy was astonishing, almost unimaginable a decade earlier. But the bomb sight's revolutionary promise was limited by Navy doctrine, which focused on attacking ships at sea. The Navy mainly used bombs as anti-shipping weapons. Attacking land targets was the Army's job, and the Army Air Corps, skeptical of Navy equipment and doctrine, showed little interest in Norden's invention. That changed dramatically in 1933. In 1925, Brigadier General William "Billy" Mitchell, a controversial advocate for air power who publicly criticized military leadership, was court-martialed. Yet his ideas, using bombers to destroy enemy industrial capacity rather than simply support ground troops, gained traction. By the early 1930s, a generation of air officers believed strategic bombing could win wars independently of land forces. But strategic bombing required hitting specific industrial targets, not just scattering bombs over a wide area. That demanded precise bombing technology. In 1933, the Army Air Corps tested the Norden Mark 15 at Aberdeen Proving Ground in Maryland. The results convinced Air Corps leaders that strategic bombing might be practical. If bombers could reliably hit factories, power plants, and transport hubs, they could systematically destroy an enemy's ability to wage war. The Air Corps then requested access to Norden bomb sights for its new bomber program. The Navy resisted. They had paid for Norden's work and saw the bomb sight as a naval weapon. They did not want to share the technical advantage with the Army. But with rising militarism in Europe and Asia, President Franklin Roosevelt intervened. In 1934, Roosevelt ordered the Navy to supply Norden bomb sights to the Army Air Corps. The Navy agreed, but insisted it would keep strict security control. That decision changed the bomb sight from a specialized naval tool into a core part of American strategic bombing doctrine. New heavy bombers, like the Boeing B-17 Flying Fortress, would carry Norden sights. The doctrine emphasized high-altitude, daylight precision bombing. Training programs were created so bombardiers could use the complex device reliably. Security around the bomb sight became extreme. The device was classified at the highest secrecy levels. Its official designation revealed nothing about how it worked, and its very existence was officially denied. Production took place in guarded factories. Parts were made by workers who were not told what they were building. Finished bomb sights were stored and shipped in locked crates under military escort. Planes were kept in hangars with armed guards. Bombardier training included strict secrecy rules. Trainees learned to operate the bomb sight before they were even told its name. Training units used practice versions that left out the manufacturer's name. Recruits signed oaths under threat of court-martial, promising not to discuss any technical detail with outsiders, even other service members. They were taught that if capture looked likely, their first duty was to destroy the bomb sight, not to save themselves. Many followed that rule. Some activated the destruction device, even though it meant almost certain death. Each bomb sight carried a small thermite grenade in a bracket mounted right behind the mechanism. Thermite, a mix of aluminum powder and iron oxide, burns at about 4,000 degrees F, hot enough to melt steel. When detonated, The grenade would destroy the bomb site in seconds, rendering it useless to the enemy. Crews were trained to arm the grenade and destroy the device before leaving a damaged plane. Failure to destroy a bomb site before capture could lead to a court-martial. Discussing technical details with unauthorized people could also lead to prosecution. During the program's early years, the security classification around Norden's work was even stricter than many Manhattan Project facilities. Why such extreme secrecy? The bomb site was more than a targeting tool. It embodied a whole strategic idea. If America could hit industrial targets precisely from high altitude in daylight, no factory would be safe. Power plants, refineries, rail hubs, and factories could be systematically destroyed, crippling an enemy's ability to wage war. If that power were perfect, it might win a war without a ground invasion. But if the enemy captured Norden technology, they could copy it to build their own precision bombs or design defenses against American bombing. Worse, German or Japanese forces could use similar accuracy to hit American cities and industries. That risk made the United States guard the bomb site with extraordinary secrecy. Fighting against high-altitude precision bombing required specially designed radar and fire control systems. These defenses could make the whole idea of precision bombing ineffective. Security didn't only protect a device, it protected a whole strategic idea. Meanwhile, Carl Norden kept improving his invention. The bomb sight that went into production in 1938, the M series, represented about 15 years of improvements over the original Mark I, II, and III designs. It used stronger motors and better gyroscopes for improved stability, temperature compensation with bimetal parts, automatic wind calculations using multiple airflow measurements, simpler controls to cut down bombardier training time, better materials, and more precise manufacturing to raise reliability. By 1940, when the Norden M9 entered service, the device was at the peak of mechanical computing technology. Its 58 precision gears were all connected, so the system continually carried out the integrations and differences needed to solve the bombing equations. The gyroscopic platform maintained stability within 1/10 of a degree regardless of the plane's attitude. Its optical system gave up to 8 times magnification with image quality comparable to expensive binoculars. The electrical interface to the autopilot allowed very small course corrections, about 1/10 of a degree. Production was a huge challenge. Each bomb site required about 2,000 separate parts, many machined to tolerances only the best tools could make. Assembly took skilled technicians about 35 hours per unit, and every part was tested before installation. Quality control failures meant about 15% of assembled bomb sites were rejected. Accepted sites went through final testing in fixtures that simulated flight conditions. By 1941, as America's entry into World War II looked increasingly likely, production accelerated. Norden's company and Sperry Gyroscope together hired about 8,000 workers to make sights and parts. By December 1941, production reached 50 units per day, and plans aimed for 200 units per day by mid-1942. The cost was enormous. In 1941, each Norden bomb sight cost about $8,000, roughly $150,000 in today's dollars. For comparison, a whole B-17 bomber cost about $200,000 then. A Norden sight, therefore, represented about 4% of a bomber's cost. During the war, the U.S. spent over $400 million to produce nearly 50,000 Norden bomb sights, making it one of the most expensive single-weapon programs of the war. Was the investment worth it? The answer would be tested over Germany, where American strategic bombing doctrine faced its sternest trial. In 1942, the 8th Air Force, based in England, tried something unprecedented: daylight precision bombing of German industrial targets from high altitude. The idea was that heavily armed B-17s and B-24s would fly large formations, remain above much anti-aircraft fire at 20,000 feet or more, and use Norden sights to hit factories and other specific targets. If it worked, strategic bombing could cripple Nazi war production without a ground invasion. Reality was more complicated. In late 1942, Early American heavy bomber raids over Europe hit French targets with little resistance, and the Norden performed impressively in ideal conditions. Bombardiers could often place bombs within 500 feet of a target from 25,000 feet, but missions over Germany exposed problems designers had not fully anticipated. High-altitude bombing meant operating above 20,000 feet, where temperatures could drop to -40 F. Despite heaters, Norden's precise mechanisms sometimes frosted up. Optical parts became hazy, lubricants thickened, and gyroscopes slowed. A sight that worked perfectly at 15,000 feet in warm California tests could fail at 28,000 feet over Germany in winter. German fighters attacked bomber formations before they reached bombing altitude, forcing evasive tactics that disrupted the careful, steady setup Norden system needed. Computing a correct release point required minutes of stable flight before the drop. Fighters deliberately broke up formations and pummeled them, trying to prevent that calm setup. Bombardiers and crews had to balance keeping formation and setup time against surviving the defensive attacks. Meanwhile, German flak, heavy bursts of anti-aircraft fire, produced violent jolts that shook the aircraft and the bombsight, further complicating accurate aiming. Norden's gyroscopic platform could handle normal turbulence, but multiple nearby flak bursts could overwhelm the stabilization. Bombardiers reported that close explosions would throw their plane around the sky, making it hard to keep the target in view. Cloud cover, common in northern Europe, often hid targets completely. The Norden was an optical instrument and needed a clear visual of the target. Clouds meant canceling the mission, attacking a secondary target, or worse, dropping bombs through clouds at a guessed location with only a small chance of accuracy. Strategic bombing theory assumed clear weather, something that often didn't happen over Germany. Equally important, Norden's accuracy depended on precise, up-to-date input data. Altitude had to be exact, wind speed had to be correct, wind measurements had to be current, target coordinates had to be precise, but high-altitude maps over Germany often differed from sea-level charts. Airspeed indicators could be wrong. The weather and wind changed constantly. Intelligence reports sometimes gave incorrect target locations. Every small input error could become a much larger targeting error. Despite these challenges, Norden helped make strategic bombing plausible. Statistical analysis from 1943 onward showed that Norden-equipped bombers achieved circular error probabilities far better than before. In combat, about 50% of bombs from 25,000 feet fell within a roughly 1,000-foot radius. That was 10 times better than the best German or British heavy bombers and good enough, when consistent, to hit large industrial targets. More importantly, Norden allowed the concentration of bombs on specific buildings within larger complexes. Instead of carpet bombing an entire city, American bombers could focus on particular factories. The famous Schweinfurt, Regensburg missions in August and October 1943 specifically targeted ball-bearing factories. Norden sites let bombardiers aim at particular buildings inside factory complexes, doing maximum damage to vital production facilities. German intelligence urgently wanted Norden technology. They knew American bombing accuracy was surpassing Germany's defenses. Captured American bombardiers were questioned about their bomb sites. Luftwaffe pilots were ordered to attack the noses of bombers where the bomb sites were installed, to try to damage them. German agents in neutral countries tried to bribe workers at Norden production sites. German military intelligence made acquiring a Norden bomb site a top priority. Security worked. Even though thousands of bombers were lost over Europe, very few intact Norden bomb sites fell into German hands. Bombardiers, true to their training, destroyed the devices before capture. Most examples the Germans obtained were so damaged by thermite grenades, crashes, or combat that reverse engineering was impossible. The device's extreme precision meant even slight damage made it useless. Germany did capture a few relatively intact examples. In March 1943, a damaged B-17 landed in neutral Sweden. Swedish authorities seized the plane and its equipment, including a Norden bomb site. Through German intelligence, diplomacy, and secret operations, the Germans obtained photographs and some technical details before the Swedes returned the plane to American control under Allied pressure. German technical reports preserved by the Luftwaffe intelligence section show two conclusions. They respected Norden's sophistication, and they could not reproduce it. German engineers correctly identified the core principles: gyroscopic stabilization, continuous mechanical computation, and autopilot integration, and admired the production precision and design elegance. But they reached a sobering verdict. With available resources and industrial limits, Germany could not copy Norden's required tolerances in sufficient numbers. Their gyro technology lagged behind America, and they could not match the precise manufacturing Norden required. German optical production was good, but they could not make the high-quality mechanical computing parts that the Norden required. Most critically, Germany lacked the special alloys and materials needed to make components that would work reliably at -40 F. The German report concluded it would take at least 3 years and large resource expenditures to copy Norden's device, something Germany could not afford. Their recommendation was to focus on disrupting American bombing with fighters and flak, rather than trying to match American bombsight technology. That judgment effectively admitted U.S. technical superiority in precision bombing, even before the final wartime statistics on Norden's impact were known. If you're enjoying these classified WWII stories, be sure to subscribe to the channel. You don't want to miss what's next. Japan also failed to capture usable Norden technology. Although many American bombers were shot down in the Pacific, intact bomb sites rarely fell into Japanese hands. Most damaged aircraft sank in the ocean, taking the bomb sites with them. Surviving bombardiers usually destroyed their sites before capture. Japanese intelligence recovered bits and pieces from wrecks, but never enough complete examples to reverse engineer the device. Japanese bombing technology lagged behind both American and German standards. Japanese bombers relied on simpler optical bomb sights with manual calculations. Their accuracy was low by American standards, though sufficient for area bombing over Chinese cities. The Japanese Navy developed somewhat better sights for torpedo bombers, but those were for anti-ship attacks, not strategic bombing. As the war went on, Norden bombsight technology continued to improve based on feedback from combat crews via intelligence channels. In 1944, the M9A added better temperature compensation and stronger gyros. The M9B added improved optics for foggy conditions. Production also rose dramatically. By 1944, Norden and Sperry together were making more than 450 bomb sights per day. The device equipped virtually every American heavy bomber and many medium bombers in both the European and Pacific theaters. By the end of the war, total production exceeded 50,000 units, costing more than $400 million. Training bombardiers to use the Norden required extensive schooling. The Army Air Forces set up bombardier schools across the United States, with a main training facility at Midland Army Airfield in Texas. The standard bombardier course lasted 12 weeks and covered optical principles and telescope use, mechanical computer operation and maintenance, bomb run math and ballistics, dead reckoning navigation at high altitude, mission planning and target analysis, emergency procedures, and security protocols. Trainees practiced first on ground-based training rigs, then on flying training aircraft over targets in the American Southwest. Only after demonstrating consistent accuracy did a trainee earn a combat bombardier rating. The dropout rate was over 30%. Using the Norden effectively required math ability, steady nerves, and attention to small details, a combination not everyone had. Qualified bombardiers continued to practice throughout their careers. Between missions, they flew training flights to rehearse airflow measurements, altitude corrections, and emergency procedures. The 8th Air Force set up practice ranges in England so bombardiers could keep their skills sharp by bombing mock targets under combat conditions. Poor performance in training could lead to extra instruction or removal from combat duty. The emphasis on training paid off. As bombardiers gained experience, statistical measures of bombing accuracy steadily improved. Early in 1943, missions typically achieved about a 1,500-foot circular error probable. By late 1944, experienced bombardiers were regularly achieving 800-foot accuracy, and some elite bombardiers could consistently put bombs within 400 feet of a target from 25,000 feet. These gains came partly from practice and partly from tactical adaptations to the combat environment. Lead bombardier tactics let the most experienced bombardier in a formation do the aiming for the whole group. When the lead bombardier released his bombs, all the planes in the formation dropped theirs too. That created a concentrated pattern of bombs and multiplied the effectiveness of the best bombardiers while reducing the effect of less experienced crews. Offset targeting techniques allowed bombing through thin cloud layers. If the target itself couldn't be seen but nearby landmarks were visible, bombardiers would aim at the visible landmark and release with a calculated offset so the bombs would fall on the hidden target. This required detailed knowledge of the target area and exact wind data, but it let crews continue missions that otherwise would have been canceled. Post-strike photographic reconnaissance showed that strategic bombing and Norden technology worked. Major German industrial targets suffered progressive damage through 1944. Repeated Norden-guided attacks on Schweinfurt's ball-bearing factories cut output by about 67% by late 1944. By early 1945, German synthetic fuel plants had their combined output reduced by roughly 90%. The effects went beyond simple physical destruction. Precision bombing forced Germany to break up and harden its industry. Building underground factories was expensive and harder to run. Smaller, dispersed plants needed more transport and coordination. Heavy use of steel and concrete in hardened buildings diverted resources away from producing tanks and ships. Just the threat of Norden-equipped bombers forced Germany to move resources from production to defense. After the war, Albert Speer, Hitler's Minister for Armaments, said U.S. precision bombing was decisive in crippling German war production. Although German industry repeatedly recovered from attacks, continued precise bombing eventually overwhelmed repair efforts. Speer highlighted the 1944 oil campaign, where targeted attacks on synthetic fuel production helped break Germany's military ability. In the Pacific, Norden showed mixed results. From 1944-45, B-29s initially used high-altitude precision bombing similar to Europe and performed well against Japanese industrial targets that were more lightly defended than German ones. But Japan's weather, strong high-altitude winds, jet streams, and frequent cloud cover caused new problems. Wind speeds over 200 mph at bombing altitudes made accurate wind calculations very hard. Clouds were more common than in Europe, so target obscuration was a big issue. By early 1945, B-29 operations shifted mostly to low-altitude, night incendiary raids, where Norden's precision mattered less. The atomic bombing missions of August 1945 also used Norden sights. On the Enola Gay, Bombardier Major Thomas Farabee used his Norden to place the Hiroshima bomb within about 100 meters of the aiming point from 31,000 feet, demonstrating Norden's capability even in the most consequential strike. Post-war debates about Norden's effectiveness are lively. Critics point out that combat accuracy was far below the idealized test claims. In combat, the circular error probable CEP was typically 801,000 feet, not the 50-foot test figures. Only about 20% of bombs dropped from high altitude hit within 1,000 feet of the aim. The other 80% were spread much more widely. Defenders argued comparisons with test conditions were misleading. Combat missions faced poor weather, bad target coordinates, and heavy enemy attacks that made ideal settings rare. It was striking that, even in difficult conditions, bombs often landed within a quarter-mile of the aim point. Though perfect accuracy was rarely achieved, Norden made precise strategic bombing possible. The debate over cost-effectiveness was complex. Spending $400 million for 50,000 sites sounds expensive, but during the war, it was less than half of 1% of total U.S. military spending. If Norden's sites helped shorten the war by weeks, they may have saved more money and lives than they cost. Critics asked, what if there had been no precision bombing? That question supports the idea that the investment could be justified. Carl Norden himself stayed largely out of the public eye during the war. Security rules kept him hidden. He continued improving the sites and working on other military projects at his New York facilities, but he received no public honors during the war years. In 1946, he received the Navy's Distinguished Service Medal, his first public recognition, but security rules still limited how much could be said about his work. Norden had mixed feelings about his invention's wartime use. A perfectionist who demanded extreme accuracy, he was disappointed that combat rarely matched the precision he believed possible. He blamed imperfect training, poor maintenance, and tactical misuse rather than his design. He spent the latter years trying to develop improvements that were never adopted. He remained convinced that his sights could reach true test range accuracy if only the military accepted his fixes. Legal questions around Norden's early development were never fully settled. His 1915 work, while employed by Sperry, clearly broke his employment contract. He used company resources, research, and facilities without permission. Under strict modern interpretations of employment and intellectual property law, Sperry could have had a strong claim. The Navy's negotiated settlement likely prevented long, public lawsuits that might have delayed the bombsight's development. So, was Norden a criminal? Legally, he violated his contract and misused company assets, but his actions were driven by frustration with bureaucracy and a belief that his design was vital for national defense. He risked his career and livelihood to pursue what he thought was a crucial military technology. Whether that was right depends on whether you value strict rule following or the breakthroughs that sometimes come from bending rules. Norden's story shows that major innovations can come from people willing to break rules for what they believe in. The Norden bombsight continued to serve after World War II, through the Korean War, and into the 1950s. B-29s in Korea used Norden sights for precision attacks, and bombardier training continued. The strict security classification lasted until about 1955. New technologies slowly made optical bombsights obsolete. Radar bombing systems and guided weapons worked in cloud and darkness and did not need a human to visually aim. By the late 1950s, jet bombers flew at speeds and altitudes where optical bombing was impractical. The last active Norden sights were removed from service in 1957, ending a 37-year career for the device. Many were scrapped. A few were deactivated and placed in museums. A few Norden bombsights were preserved for training purposes, and today perhaps a dozen remain in museums around the world. These artifacts represent a technology once considered even more secret than the earliest nuclear weapons. Carl Norden passed away on June 14, 1965, in Zurich, Switzerland, at the age of 85. Freed from wartime security restrictions, his death notices were finally able to highlight his achievements. The New York Times called him the man whose invention helped win World War II. Navy Times credited him with giving America the weapon that destroyed Nazi war-making capability. Aviation Week described the Norden bombsight as the most important aircraft accessory of the war. In a rare 1960 interview, Norden himself was more modest. "I created a device that did what it was designed to do. Whether it was used as effectively as possible, I cannot say. I am an engineer, not a military strategist. I solved a technical problem. Others decided how to use that solution. I hope it helped end the war sooner and saved lives. That was always my intention." The legacy of Norden's unauthorized invention extends beyond its military impact. The bombsight represents one of the most sophisticated mechanical computers ever built, pushing manufacturing technology to its limits. The precision manufacturing techniques developed for its production influenced post-war industries from electronics and automation to aerospace. Quality control systems established to ensure bombsight reliability became industrial standards. Norden's pioneering gyroscopic stabilization technology influenced countless applications, from aircraft instruments to missile guidance to spacecraft navigation. Modern inertial navigation systems, which allow planes and ships to determine position without external references, descend directly from Norden's gyroscopic platform. Integration of computing devices with aircraft flight controls, first achieved in the Norden bombsight, set the standard for all modern aircraft. Perhaps most importantly, the bombsight demonstrated that precision-guided weapons could fundamentally change warfare. The ability to hit specific targets from a safe distance, rather than relying on saturation bombing, opened new strategic possibilities. Modern guided munitions, from laser-guided bombs to cruise missiles and GPS-guided weapons, follow the conceptual path pioneered by Norden. Whether Norden's illegal development methods were justified depends ultimately on outcomes. Without his unauthorized work at Sperry, the revolutionary bombsight might never have been invented. By taking legal risks, he made American strategic bombing possible. His obsessive perfectionism forced him to work secretly, even in violation of his employment contract. Allied victory might have taken longer or cost more lives without him. The U.S. government recognized Norden with the Distinguished Service Medal and allowed him to profit from his invention through royalties. In retrospect, the illegal origins of his work were overlooked because the results were so consequential. Results triumphed over rigid rules, establishing a complex precedent. In matters of technology, should personal conviction override contractual obligations and legal restrictions? Can illegal acts be excused if national security demands it? When outcomes contribute to national safety, should their fairness be assumed? There are no simple answers, but Norden's story forces us to consider them. Modern military innovation still occurs under multiple constraints. Employment contracts define intellectual property, government security clearances carry legal obligations, and classified research is conducted in secure facilities. Unauthorized development like Norden's would be far more difficult today and carry far greater legal consequences. Whether such constraints foster or hinder innovation remains debated. Still, the fundamental tension Norden experienced between bureaucracy and creative insight persists. Oversight that ensures accountability can also slow innovation, and security measures that protect classified information can isolate researchers from critical insights. Contractual provisions designed to protect an employer's interests can also discourage individuals from pursuing groundbreaking ideas. Striking the right balance has always been challenging. The Norden bombsight stands as evidence of both the power of personal talent and the importance of supporting innovation, even when it emerges through irregular channels. Carl Norden's unauthorized invention became America's secret weapon because he valued technological potential over strict adherence to rules. Whether viewed as heroic or criminal, patriotic or defiant, it depends on perspective, but the historical outcome is undeniable. His device helped win World War II. The story of the Norden bombsight reminds us that sometimes the greatest achievements come from those willing to break the rules in pursuit of their convictions. Norden's technical genius, combined with his relentless dedication, overcame legal restrictions and bureaucratic obstacles. This combination of talent and passionate determination produced a weapon that altered the course of the war and decisively contributed to Allied victory. Today, when you see images of B-17s and B-24s flying over Europe, remember that in the cockpit of each bomber sat a device that, arguably, should not have existed. It was an invention born from stolen time and unauthorized work, a weapon created in violation of employment contracts and corporate policy, a secret more closely guarded than nearly any other American military technology, yet a tool that helped topple Nazi rule. It proved that precision strategic bombing could win wars. Carl Norden's illicit creation became America's secret weapon because, even when revealed irregularly, talent and passion can produce outcomes that transcend the rules being broken. The Norden bombsight demonstrated that technological excellence in the service of a critical need can overcome questionable origins. It also showed that sometimes the most important innovations do not follow the proper channels. They come from those willing to risk everything for ideas they believe will change the world.